Alright, so we will continue with network address translation, which we left off from our proxy firewall topic. Network address translation. The most common use case for a NAT is when a site within a single internet connection is assigned a small range of IP addresses, perhaps only a single address, but there are multiple computers requiring internet access. When all incoming and outgoing traffic passes through a single NAT device that partitions the inside private address realm from the global internet address realm, all the internal system can be provided internet activity as clients using locally assigned private IP addresses, allowing privately addressed systems to offer services on the internet, however, is somewhat more complicated. So not, it's a complex thing, but we will dig into its properties to better understand it. So in a big picture, not 80% of the internet still use NAT or end devices. So let's say you have like 40% traffic coming from home and 60% coming from data center, CDN, etc. That 40% traffic in the internet or the endpoints mostly use NAT. So we will discuss that further here. Basically, like 20% of the internet only use IPv6, or 80% of the internet still use the IPv4. So they require NAT because IPv6 doesn't require NAT. So it basically hide its private addresses from the outside world and only communicate the NAT through a public interface. So only communicate to the public world through its public interface. It's the same with mobile as well. So for laptop, for home Wi-Fi, for mobile data, they also use CGNAT, which we discussed in the previous video. So CGNAT is the kind of like a double NAT of most home routers today. So they provide a single IP that provides access to the private host within a Wi-Fi or data. NAT is popular because it reduces the need for globally routable internet addresses, but also because it offers some degree of natural firewall capability and requires little configuration. So the reason why it is in firewall section as well is because these NAT automatically provide firewall configurability. Firewall features. It's just different the way the granularity of how it will restrict the traffic. Perhaps ironically, the development and the eventual widespread use of NAT has contributed to significantly slow adoption of IPv6. Despite its popularity, NAT has several drawbacks. The most obvious is that offering internet accessible services from the private side of a NAT requires special configuration because privately addressed systems are not directly reachable from the internet. So these are the disadvantage or the property as well of NAT that will help us better understand it. Because NAT needs a configuration, or you're not contacting the private address directly, unlike IPv6, of course there's a disadvantage. But most of it are just using TCP port. So that's another property to understand NAT, is to be able to discuss how it interacts with different kind of ports such as TCP, UDP. So for UDP, we have an entire long section later, especially for next videos for real-time video. So we also have that. Despite its popularity, NAT has several drawbacks, right? The most obvious is that offering internet accessible services from a private side of NAT requires special configuration because privately address systems are not directly reachable from the internet. So in the future video, we will dig into these details on how we actually configure different NATs in different networks. But the same statistics remains. This 80% are using TCP because that's the reason why we're discussing this book. It's TCP over IP, and the other traffic are using UDP for real-time communication. In addition, for a NAT to work properly, every packet in both direction of a connection or association must pass through the same NAT. This is because the NAT must actively rewrite the addressing information in each packet in order for communication between a privately addressed system and a conventionally addressed internet host to work. In many ways, NATs run counter to a fundamental tenet of the Internet Protocol, the smart edge and dumb middle. To do their job, NATs require connection state on a per association or per connection basis and must operate across multiple protocol layers unlike conventional routers. So for conventional routers, remember you only can only work in a specific layer protocol. For NAT, they need to work for TCP, UDP. They also need to work for SC turn, which we will discuss in the next video. So those are the different configuration, and one of its basic property as well is it has a memory that maintains the connection state. So we kinda touch on this in the previous video as well. In a per connection, so modifying an address at the IP layer also requires modifying checksums at the transport layer. So if you modify it in layer 3, so since not change the IP address to its public IP, like we discussed in the previous video, it will change the checksum of that IP packet, and then it will change the layer 4 packet as well. Now we're getting to get some of introduction of the transferred layer, but we will discuss that in more detail in the future video in chapter 10 and 13 regarding the pseudo header checksum to CY. NAT poses problems for some application protocols, especially those that send IP addressing information inside the application layer payload. So some protocol, however, send an IP addressing information, kind of like IP related, inside the application layer, which is the layer 7. The File Transfer Protocol, FTP, and SIP are among the best known protocols of this type. So this is another property of NAT, is that for this type of protocol, they are actually you need more configuration. So they require a special application layer gateway function that rewrites the application content in order to work unmodified with NAT, or other NAT traversal methods that allow the applications to determine how to work with the specific NAT they are using. A more complete list of considerations regarding NAT appears in RFC 3027. So these are just the basic properties. In reality, in real world, most of them works like this because most of them is a home network. But if you really want to know how NAT works, you need to go here in RFC 3027 because they discuss the common behavior of different NATs. Despite their numerous problems, NATs vary widely, and most network routers, including essentially all low-end home routers, support it. So most low-end routers. For middle and then enterprise level, that's where you get more nuance or more uncommon ways to operate NAT. But it's just because they have different application. Today, NATs are so prevalent that application designers are encouraged to make their applications NAT friendly. It is worth mentioning that despite its shortcomings, NAT supports the basic protocols, i.e., email, web browsing, that are needed by millions of client systems accessing the internet every day. So, again, it's not emphasizing that despite these shortcomings of NAT or disadvantage of its properties, it's still the most commonly used today, for especially for low end, or 80% of the traffic for endpoint is a low end, and when you consider that 80% of the internet is also TCP, it is the most commonly used. That's the reason why, again, discussing this. A NAT works by rewriting the identifying information in packets transiting through a router. Most commonly, this happens for two direction of a data transfer. In its most basic form, NAT involves rewriting the source IP address of packets as they are forwarded in one direction, and the destination IP address of packets traveling in the reverse direction. See figure 7.3. This allows the source IP address in outgoing packets to become one of the NAT's router's internet-facing interfaces instead of the originating host. Thus, to a host on the internet, packets coming from any of the hosts on the privately addressed side of the NAT appear to be coming from a globally routable IP address of the NAT router. Figure 7.3. A NAT isolates private addresses and the systems using them from the internet. Packets with IP addresses are not routed by the internet directly, but instead must be translated as they enter and leave the private network through the NAT router. Internet hosts see traffic as coming from a public IP address of the NAT. Most NATs perform both translation and packet filtering. So aside from translation, which is the tracking its connection per connection, include the tracking per connection, because this NAT has memory as discussed. It also has the packet filtering, so it's kind of like works in two ways. So for discussing firewall in networking, you always need to consider NAT, because this is most commonly used in the internet to connect traffic outside. So in order to understand firewall, you really need to understand how different NATs are configured with different transport protocol, which again needs you to understand the introduction or some level of transport layer. And the packet filtering criteria depend on the dynamics of the NAT state. The choice of packet filtering policy may have a different granularity. For example, the treatment of unsolicited packets, those not associated with packets originating from behind the NAT, received by the NAT, may depend on source and destination IP address and or source and destination port number. The behavior may vary between NATs, or in some cases vary over time through the same NAT. Traditional NAT, basic NAT, and NAPT. The precise behavior of NAT remain unspecified for many years. Nonetheless, a taxonomy of NAT types has emerged, based largely on observing how different implementations of the NAT idea behave. The so-called traditional NAT includes both basic NAT and network address port translation. So these are the basic properties of NAT. To understand NAT, here's one of the keys, is to understand what are the traditional NAT and the basic and the network address port translation, NAPT. So basic NAT performs rewriting of IP address only. In essence, a private address is written to be a public address, often from a pool or range of public addresses supplied by an ISP. This type of NAT is not the most popular because it does not help to dramatically reduce the need for IP addresses. The number of globally routable addresses must equal or exceed the number of internal hosts that wish to access the internet simultaneously. A much more popular approach, NAPT, involves using the transport layer identifiers, ports for TCP and UDP, query identifiers for ICMP, to differentiate which host on the private side of the NAT is associated with a particular packet. See figure 7.4. So here, a basic IPv4 NAT left rewrites IP address from a pool of addresses and leaves port numbers unchanged. NAPT right, also known as IP masquerading, usually rewrites address to a single address. NAPT must sometimes rewrite port numbers in order to avoid collisions. So instead of just rewriting the IP address, it also rewrite the port sometimes to avoid collusion. So this is one of the characteristic of the NAT that we were gonna discuss. Of course, there's more nuance on this depending on different application, but these are the basics. To differentiate which host on the private side of the NAT is associated with a particular packet, this allows a large number of internal hosts, multiple thousands, to access the internet simultaneously using a limited number of public addresses, often only a single one. The address used in private addressing realm behind or inside a NAT are not enforced by anyone other than the local administrator. Another property or another thing is that for basic NAT, the local administrator can choose whatever he wants, but there's a catch because you must choose from a range of private IP that was allocated using like the IANA, so like we discussed in the previous video. So however, when such global addresses are owned and being used by another entity on the internet, local systems in the private realm would most likely be unable to reach the public systems using the same addresses because the close proximity of the local systems would effectively mask the visibility of the farther away systems using the same addresses. To avoid this undesirable situation, there are three IPv4 address ranges reserved for use with private addressing realms: 10.0.0.0/8, 172.16.0.0/12, and 192.168.0/16. This is the reason why you see those local addresses at your home. These addresses range are often used as a default values for address pools in embedded DHCP servers. As I suggested earlier, so DHCP servers, we discussed that in the previous video, but basically those are the one that provides the IP or the address range used in default values for such address pools, but that's the end of its relationship with NAT. Okay, so for NAT to really understand NAT, in the next video we will discuss how those like rare NAT that talks to real-time application like P2P, like games or real-time video, actually work, because those are more complicated. As suggested earlier, a NAT provides some degree of security similar to that of a firewall. By default, all systems on the private side of the NAT cannot be reached from the internet. Consequently, communications between hosts in the private addressing realm and those in the private public realm can be facilitated only with participation from the NAT according to its usage policies and behavior. So another thing is the NAT has its different usage policies, but the most common is all outgoing is allowed, and the incoming is only for TCP, UDP, and the common ports. While large variety of policies may be used in practice, a common policy allows almost all outgoing and returning traffic associated with outgoing traffic to pass through NAT but blocks almost all incoming new connection requests. This behavior inhibits probing attacks that attempt to ascertain which IP addresses have active hosts available to exploit. In addition, a NAT, especially a NAPT, hides the number and the configuration of internal addresses from the outside. As we shall now explore, NATs are tailored to the protocols and applications that they need to support. So it's difficult to discuss NAT behavior without also mentioning the particular protocols it is being asked to handle. Thus, we now turn to how NAT behaves with each major transport protocol and how it may be used in mixed IPv4 or IPv6 environments. Many of the behavioral specifics of NATs have been the subject of the IETF Behavior Engineering for Hindrance Avoidance Behave Working Group. Behave has produced a number of documents starting in 2007 that clarify consistent behavior of NATs. NAT and TCP. Recall from Chapter 1 that the primary transport layer protocol for the Internet, TCP, uses an IP address and port numbers to identify each end of a connection. A connection is identified by the combination of two ends. Each unique TCP connection is identified by two IP address and two port numbers. So these are the most back to understand or most value to understand. So for this, since this is the most useful, the basic mechanism for TCP over IP is that you have two source port numbers for NAT and you have two source IP address. When a TCP connection starts, an active opener or client usually sends a synchronization packet to a passive opener or server. So this is what happens when you're browsing in your Google Chrome. It sends this first a SYN packet. The server responds with its own SYN packet, which also includes an acknowledgement of the client SYN. So the server, or the one you enter as a website, will send a SYN or will respond with its own SYN packet with its own source IP and source port number alongside an ACK bit, so another thing that it will send aside from SYN that acknowledges the client SYN. The client then responds with an ACK to the server. So after that, the client now will send only ACK, no SYN bit. The three-way handshake establishes the connection. So that's what we call the three-way handshake. A similar exchange with finish packet is used to gracefully close a connection. So in case like you close the browser, you exit the tab, it will send that bit, and then it will acknowledge the receiver will send the FIN bit with an acknowledgement, and the client will send an acknowledgement as well. The connection can also be forcefully closed right away using a reset packet. So sometimes you're still doing something and you need to force it to close it forcefully, like turning off the PC or something happened on your laptop that it made it turn off, etc. So RSTC Chapter 13 for more detail on TCP connection. The behavioral requirements for traditional NAT with TCP are defined in RFC 5382 and relate primarily to the TCP three-way handshake. Referring to the example home network in figure 7.3, consider a TCP connection initiated by the wireless client at 10.0.0.126 destined for the web server on the host www.isoc.org, which has an IP address IPv4 address 212.110.167.157. Using the following notation to indicate IPv4 addresses and port numbers: source IP : source port destination IP colon destination port. The packet initiating the connection on the private segment might be addressed as 10.0.0.126 colon 9200 semicolon then 212.110.167.157 colon 80. The NAT or firewall device acting as the default router for the client receives the first packet. The NAT notices the incoming packet is a new connection because the SYN bit in the TCP header is turned on. If policy permits, which it typically does because this is an outgoing connections, the source IP address is modified in the packet to reflect the routable IP address of the NAT router's external interface. Thus, when the NAT forwards this packet, the addressing is 63.204.134.177 colon 9200 semicolon then 212.110.167.157 colon 80. In addition to forwarding the packet, the NAT creates internal state to remember the fact that a new connection is being handled by the NAT, called NAT session. At a minimum, this state includes an entry called a NAT mapping, containing the source port number and IP address of the client. This becomes useful when the internet server replies. The server replies to the endpoint 63.204.134.177 colon 9200. The external NAT address using the port number chosen by initially by the client. This behavior is called port preservation. So this keeping the port in the memory just so you can know how who client or what device sent that request is called port preservation. By matching the destination port number on the received datagram against the appropriate NAT mapping, the NAT is able to ascertain the internal IP address of the client that made the request. In our example, this address 10.0.0.126, so the NAT rewrites the response packet from 212.110.167.157 colon 80 and 63.204.134.177 colon 9200 to 212.110.167.157 colon 80 semicolon to 2 then 10.0.0.126 colon 9200 and forwards it. The client then receives a response to its request and for most purposes is now connected to the server. This example conveys how a basic NAT session is established in the normal case, but not how the session is cleared. Session state is removed if pins are exchanged. So that session state in the NAT memory is only removed if you properly close it. But not all TCP connections are cleared gracefully. So this is where the RST comes from. Sometimes a computer is simply turned off, which can leave NAT mappings in the NAT's memory, even though it's not currently being used, which provide an allocation, which provides also like a load. Thus, a NAT must also remove mappings thought to have gone dead because of lack of traffic, or if an RST segment indicates some other form of problem. Most NATs include a simplified version of the TCP connection establishment procedures and can distinguish between connection success and failure. So most NAT in the internet we see provide a simplified version of this TCP connection whenever you're trying to browse something on the web. In particular, when an outgoing SYN segment is observed, a connection timer is activated. So once you request or once you go into the site, a SYN segment is observed and a connection timer will be activated. So that, remember, that's the keyword connection. And if no act is seen before the timer expires, the session state is cleared. So if the client or you did not receive, kind of like it's just loading from the server, an act, the session is cleared in NAT's memory or your like converged memory. If an act does arrive, the timer is cancelled and a session timer is created. So those connection will be closed after that ACK from the server arrived, and a new or session, so the keyword session timer, is created with a considerably longer timeout, hours instead of minutes, which is the connection has. When this happens, the NOT may send an additional packet to the internal endpoint just to double check if the session is indeed dead, called probing. So this is the normal property or behavior of NOT for most NOT or home or most TCP connection being done. After it responds NOT acknowledgement, it see an acknowledgement, it creates this session timer, and it proves it the internal host if it actually received that ACK called probing, or if just to double check if the session is indeed dead. If it receives an ACK, so if the NOT session or the NOT router itself receives an ACK, the NOT realizes the connection is still active. So the server is not the only one receive an ACK, the NOT as well, just so he knows if he will clear the connection timer and create or clear the session to avoid over allocation. If it receives an ACK, the NOT realizes that the connection is still active, resets the session timer, and thus not delete the session. So it resets the session timer to hours again and not delete the session. If it receives either no response, either after a closed timer has expired, so there's also a closed timer in which it will wait for that an acknowledgement of the device that sent the request. So after that timer has expired or an RST segment, the connection has gone dead and the state will be cleared on the router's memory. RFC 5382, a product of the Behave Working Group, notes that the TCP connection can be configured to send keep alive packets. So another implementation aside from the common ones is that this TCP from NOT could be configured to send a keep alive packets, and the default rate is 1 packet every 2 hours if enabled. Otherwise if enabled, otherwise a TCP connection can remain established indefinitely. So those are another configuration. It will send it 1 packet every 2 hours. Otherwise, a TCP connection will remain established indefinitely, or it will stay on the NOT memory indefinitely while the connection is being set up or cleared. However, the maximum idle time is 4 minutes. So if it's being set up first or being cleared at the end of its session, the maximum idle time is just 4 minutes. Consequently, RFC 5382 requires rec-5 that a NOT wait at least 2 hours and 4 minutes before concluding that an established connection is dead, and at least 4 minutes before concluding that a partially open or closed connection is dead.